In lecture 8, I said that we call a system dependent whenever one equation is a multiple of another equation. But that's not the whole story, really. And I put a little blurb or a ticker at the bottom of the screen to kind of talk about how that's not exactly accurate. But I wanted to get into more detail with that. Now, the idea comes, the reason that we call it a dependent system comes from the idea of linear dependence and linear independence. So before we get to that, let's just talk about what a linear combination is. So we've already seen linear combinations of single variables. They look like this. That's one of them. We have a single number we have a single number x. We're multiplying it by 2, and then we have a single number y. We're multiplying it by 3. We're adding these things together. Another linear combination might look something like this right here, right? We have 3 variables. These are 3 single numbers that we can combine in some way. And we call this linear because, well, it kind of makes us think about a line, right? We know like a line equals mx plus b. We could rearrange this. We could also say that given these 2 variables, this is not the same b, but given 2 variables, you could multiply one variable by any number, multiply another variable by any number. You could add them together. They can be equal to some kind of constant, and what you have is a line, right? Adding one more variable into the mix, well, some number d, that gives you a plane, which is kind of like what you get if you took 2 lines in space, like if you imagine the y-axis and the x-axis, and if you were to drag the y-axis all along the x-axis, you would have a plane, right? And we can imagine this being in 3-dimensional space somewhere, oriented in whichever way. The linear combination is when you using only addition, subtraction, and multiplication by constant variables, or rather taking your variables and multiplying them by constants, then what you end up with is something we call a linear combination. Now, you can't have your variable being multiplied by itself or 2 variables being multiplied by each other. The thing that you end up with, we're not going to call linear anymore. And if you were to combine these things, this is no longer what we call, say, a linear combination. This would be nonlinear, and you can kind of see what we mean by that. Like if you were to solve this for y, say, you would get something like this. Let's see, xy equals 1 minus x squared, divide through by x. We get 1 minus x squared all over x. And if you were to graph that, you could easily see that that is not linear. It doesn't look anything like a line. Also, it doesn't have certain properties that we're not really going to get into right now, but that's the general idea. As long as you have some number of variables, right, and you're multiplying them by just constant values, you could do that. You could add them or subtract them from each other. Then we call that a linear combination. Now, here's the cool thing, is that linear combinations don't need to stop with just variables. If I had any functions, let's say we have a function of t, f of t, and it could be anything, right? It itself could be nonlinear. It could be something exotic. I don't know, maybe something like the square root of t over 3 raised to the t or something like that. But I'm not going to worry about what it could or couldn't be. But if we just had, let's say, 2 functions of a variable, we could say, well, we could use these and make a linear combination of them. We could say multiply the first function by some constant number. We could add that to some constant multiple of the second function. And what we have is a linear combination of these two functions. Another thing we could do is have, let's say, these things that we're using, they don't need to be variables of a single number. They don't need to necessarily be functions. They could be something we call vectors. Vectors you could think about as a point in either the plane, which this right here would be the point 1, 2, would be that point right there. We usually think about it as an arrow extending to it. It could be a point in space. It could be a point in three-dimensional space. So if we have an X, a Y, that looks terrible, a Y and a Z direction, then moving over 1 in the X direction, moving over 2 in the Y direction, and then moving up 3 in the Z direction would be that point in space. And we could think about that as a vector, which we usually draw as a line going from the origin to the point itself. But you could also represent it as just merely the point out in space. And then we could talk about linear combinations of vectors. So if we have, say, two vectors, let's say these two right here, we could talk about linear combinations of vectors. We have 2 times the vector v plus 3 times the vector w. That would be a linear combination of these two vectors. So we could talk about single points, right? Single number values, real number values, is usually what we're talking about. Those, each x and each y represents a single number. We could talk about the things that we're making linear combinations of as being functions of a variable, maybe multiple variables. We could talk about linear combinations of vectors. And these would be, for every one vector, you have 3 real value points. Don't necessarily need to be real valued, but whatever. But what we're interested in right now, so I just wanted to go off on a little tangent there. What we're interested in right now are linear combinations of equations. In the same way that I took 2 times a vector plus 3 times a vector, or 2 times a variable plus 3 times another variable. Let's just real quick, let's imagine we have 2 equations, E1 and E2, whatever it happens to be. And we can make a linear combination of these 2 equations. So we have 2E1 plus 2E2 would be a linear combination of these 2 equations. Why? Well, because you are multiplying one of the equations by a constant number. You're multiplying the other one by a constant number. You're adding them together. That's perfectly fine. However, what wouldn't be a linear combination is if you have like E1 times E2 plus, I don't know, 2E1 or something like that, or maybe plus E2 squared. That would not be linear, right? In order for something to be a linear combination, you're only multiplying by scalar values. It's constant real numbers. In our case, we're going to use real numbers. Our first equation is 2x plus z equals 3. That's our first equation. And let's take our second equation. Our second equation is going to be y plus 3z equals 1. Now, okay, let's think about different linear combinations of these that we could have. Well, one possible linear combination is we take E1 plus E2. Now, what would that give me? Well, let's see. I'd like to just do it this way, right? Because I like to have it like this. So I can see all these guys. I see we have 2x plus 0x's. That just gives me a 2x. Z plus 3z, or I'm sorry, nope, I missed the y, right? 0 y's plus y is 1y. Z plus 3z is 4 z's. And then we have 3 plus 1 is 4. Okay, so now we can even call this a third equation, right? We could say there's my third equation right there. So E1 plus E2 equals E3. Now let's see what would happen if we tried to solve for X, Y, and Z. Let's see. Okay, so I'm going to put all of this into a system. Let's start with E1 here. We have E1 is 2x, 0y, 1z. So 2, 0, 1, that's equal to 3. So there's my first system, or my, sorry, my first row of my matrix. Second one is 0x's, 1y, 0x's, 1y, 3z's equals 1. Yep. Now my third equation, which is, we call this linearly dependent. This one is dependent on these two because the third is a linear combination of these two. Again, we happen to be talking about equations. This could be functions instead of this. They could be variables, whatever, right? We're kind of being abstract here, but this equation is a linear combination of these. Therefore, this equation is linearly dependent on these two equations. Okay, the last one is 2x's, 1y, 4z's equals 4. Okay, so we have this guy right here. Now, let's see what happens when I try to row reduce this guy. I want to get it into row echelon form. I'm going to start by getting the leading one right here. So I'm going to divide this entire thing through by 2. I get 1, 0, 1 half, and 3 halves. Okay, I have not changed any of these guys. Now you might have said, well, wait a second. I mean, you had a 2 and a 2. Why didn't you just take care of it right there? Well, we could have done that. Multiplying this guy through by -2, though, will give me the same thing. It's multiplying that guy through by -1, but let's just go ahead and do it. The -2 makes that guy a 2, and the 0 here, -2 times that gives me a -1. -2 kills the 2, and we get a -3. Or equivalently, I could have just taken that row and subtracted that row at the beginning. Yeah, we get that. Okay, so moving on. That is going to give me, let's see. Okay, that row hasn't changed. That row is not changing. Okay, now that kills that, gives me a 0. 1 and 0 just stays 1. 4 minus 1 is +3. 4 minus 3 is +1. And ooh, look at that. Right now, what did I do here? I took this one, I took E3 and subtracted off E1 from it. And what do you know? I got E2 out of it, right? Right? I started here, that's E3. I subtracted off E1, which in other words, we just said take E3, subtract off E1. And yeah, it's a linear combination of the other, right? We see that E2 is what we got when we take E3 and subtract off E1, right? It makes a lot of sense here that that's all we're doing. Now, well, that is E2 right there. And so when you subtract that guy, in other words, you're trying to get a 0 right here, what happens? Well, we have to multiply that guy by -1, that gives me -3, gives me -1. In other words, take this one and subtract that, and you get your row of zeros. This guy stays put. And now we have our row of zeros. And so we could see in the original, right, like I said in lecture 8, like that you'll get a row of zeros whenever you have one row as a multiple of another row. Well, that's the case in the 2x2 case, right? Because with two equations, there's only one way for one to be a linear combination of the other, because you only have two equations to deal with. The only way to combine, to have those two equations be dependent on each other is if you had one equation that you multiplied by some number to get your second equation, right? Now that we have the possibility of 3 equations, well, one could be just a direct multiple of one, but there's another way we could do it that we couldn't find, that we couldn't do, or that we wouldn't encounter in the 2x2 case, right? Now we've opened up the possibility that, oh, we have these 2 equations combined somehow to give me a new equation that it turns out, and we call this equation, it's linearly dependent on the other 2 equations. When that happens, you get a row of zeros, which means, well, your system, when we call it a dependent system, right? And what this does, really what this is this E3 here is no new information, right? It's like we have a plane somewhere in space. We have another plane somewhere else in space. They intersect to form a line, but then you don't get any new information. You can't pinpoint that line. In the 2-dimensional case, the only way that that happens is if you have a line out somewhere, and then you have some multiple of it, but then when you solve it for y, right, you end up with the exact same line. That second equation doesn't give you any new information and you're still on the same line. Here it's a little bit different. It's the same principle. You have some plane somewhere, some other plane somewhere, then you somehow do a linear combination of those planes, and the thing you get, well, it's the same. You don't get any new information by that. It's kind of like saying, you know, in the 2-dimensional case, you have the same line. Well, even with this new plane, you still have the same intersection. You don't have any new information to try to pinpoint a specific point. So that's what's going on here.
To illustrate what I'm talking about, I have plotted 2 planes here, and you can see we have the 2x plus z equals 3. That's plotted in blue. And then in pink, I've plotted the y equals 3z plus 1. And we could see that these 2 planes intersect here in a line, right? And now the way that a consistent system with one solution works is that the third plane intersects that line there, that line where the blue meets the pink. A third plane intersects that line at one point, and you can kind of see where that is. If I zoom in there, right, we can see that. And there's another way of thinking about it. You could say that line intersects the pink plane, the line made by the blue and the orange. You could say that the line that the blue and the pink make right there intersects the orange plane right there. But you can see there's only one point where those 3 planes intersect. Now, when you have a dependent system, which is the case when we add those first 2 equations together to get 2x plus y plus 4z equals 4, let's see what happens. You can see we get a new plane out of it, but it intersects the other planes in the exact same line. And that's what I meant by you get no new information. Like, yes, you have a new plane, and yes, it looks different in space, right? It's different from the pink plane. It's different from the blue plane, but the place where they all intersect is exactly the same. It's still exactly the same line. You're no nearer to finding one point.
Another example I gave in the ticker on the lecture 8 was this linear combination of these 2 equations. That's 3 times the equation E1 plus -2 times the equation E2 to give you a new equation. And let's go ahead and figure that out. 3 times E1 would be what I get when I multiply everything through by 3. That'd be 6x plus 3z equals 9. -2 times E2 would be a -2y minus 6z equals -2. Adding those all together gives me my new equation, E3, which is going to be 6x minus 2y minus 3z equals positive 7. Okay, so now let's see what happens when I put E1, E2, and E3 into a system and try to solve it. So we'll take E1 first. So that's going to be 2 x's, 0 y's, 1 z, and a 3. E2 is 0 x's, 1 y, 3 z, and a 1. E3 is now 6 x's minus 2 y's minus 3 z's equals 7. Okay, so we want to row reduce this guy. I guess we need a leading one right there. So I'm going to divide that entire equation through by 2 right there. And so that gives me 1, 0, 1 half, 3 halves. Not changing this one. And I'm not changing the last one. Now, okay. I need to kill off this 6, so it needs to have a negative 6. The way I'm going to do that is to multiply this entire row by negative 6. When I do that, I get a negative 6 and a 0. Negative 6 divided by 2 is 3, negative 3. 3 times negative 6 divided by 2 is the same thing as negative 3 times 3. It should be negative 9. Okay, now, does that look familiar? It looks real familiar. In fact, that is negative 3e1. What I'm doing here, if you notice, is I'm taking the e3 that I have, and I'm subtracting off 3 times e1, right? So what should I have left? Well, it should be negative 2 times e2. And let's just see. When I do that, we're gonna get, okay, I'm not changing the top row. 1, 0, 1 half, 3 halves, 0, 1, 3, and 1. Now that gives me a 0, a minus 2, a minus 6, and a minus 2. And is that negative 2 times E2? Yeah, it is, right? There's negative 2 times E2, negative 2 y's, negative 6z minus 2. Okay, now what would I do? If I were just going on with row reduction, I would have my column of zeros. So I go over here and say, oh, I already have a leading one. I'm good to go. So now I just need to get zeros beneath here. In order to do that, I need to add a 2 to the negative 2. So I need to multiply that entire row by a positive 2. When I do that, I get a 0, a 2, a 6, and a 2. And then I'm going to add those 2 together. So then, wait, what am I doing? I'm adding, right? So we took E3, we subtracted 3 times E1, which gave us that thing right there. And now I'm adding 2 times this right here. In fact, I'm bringing that back over, aren't I? Right? That is negative 2 times E2 is that. That would be the negative of that, or adding it to it, right? That's the same thing as saying plus 2 times my original E2. That right there is 2 times the original E2. And I'm simply adding that to that row that I had right there. Now let's see what we get. Well, you could already guess, right? We have 1, 0. That guy has not changed. This guy is not changing. And now when I do that, I get 0, 0, 0, 0. And indeed, yeah, that should be a big fat 0 right there, right? So you kind of see what ends up happening is if one of your rows is a linear combination of the other rows, then the algorithm that we've developed here, just kind of one step at a time, it undoes all of that, right? Like in order to get E3, we say you multiply E1 by 3, and then you add that to -2 times E2, and then each step of the algorithm just kind of takes that off one by one. It says, okay, we're starting here at E3. Let's take off 3 negative, we'll subtract off 3 times E1 from that guy that we had right there. And then the algorithm says, well, we're going to add 2 times the second row, which is E2, to that guy right there. And that is exactly how we get back to 0, because, well, that just comes from that right there, right? If we were just to solve or basically bring everybody over on one side. But the thing to notice is that is what the algorithm does. We didn't think about it in these terms, but it's just a consequence of the algorithm itself, is that it's going to sniff out anything that is a linear combination of other rows. And as you combine these rows together, if there is one that is a linear combination of the others, it will end up getting canceled out completely. And that's how you get your row of zeros. So like I was saying, with 2 equations and 2 unknowns, the only way to have one of them be a linear combination of the other one is, well, let's just think about this. You have to do something to E1. You can't multiply it by itself. E2 doesn't exist yet, right? We're trying to make one that is a multiple of another. So the only thing we could do is just multiply it by some constant. Let's just say 3. And when you do that, you'll get, let's see, 3x minus 3y equals -3. And we saw in lecture 8 that from here, it's easy to see that these define the same line, because you could just solve these for y, right? In the top one, you bring the y over, gives you y by itself. Bring the 1 over, and you get x plus 1. In this case, you do the same thing. You get 3x plus 3 equals 3y. Divide everybody through by 3, and you end up with the exact same equation. That just says y equals 1 plus x, which is the same thing as that, right? And so it's easy to see in the case with 2 equations. And we can see that's the only possibility to have a linear combination when you have 2 equations with 2 unknowns, right? Now when we have 3 equations, there are more than one ways of there's more than one way of making E3 a linear combination of the other 2, right? I could say, well, E3 is just E1 times 3, like I did there. I could say, well, it's also plus 2E2, and that's how, we saw that just a minute ago, how you could get something that's not a direct multiple of one of them. It's not exactly the same line, but it'll still give you a row of zeros. And your system is dependent, because one of your equations, one of your rows, is linearly dependent on the whole thing. I just want to show you that this works, or rather it doesn't work. You will get a row of zeros, even if one is indeed a multiple of one of the others. So let's just check. And this will be real easy to check. We're going to go 3 times that first one, gives me 3x's plus 3y's plus 3z's equals 3. And now if I were to put this into a system and row reduce this guy, we would have the first equation gives me 1's all across. We get 2, 0, -1, 3. Finally, we get 3, 3, 3, 3. I'm not going to go through getting that guy out of the way, because we could see what's going to happen when we do this. We'd say, okay, we need a 0 here, so that needs to be a -3. I'd have to multiply that entire row by -3. When I do that, I get -3's all the way across, and oh boy, there it is. 1, 1, 1, 1, 2, 0, -1, 3, and then -3 times that plus that does give me indeed a row of zeros. So it's not just that one equation is a multiple of another. While that will always give you a row of zeros, and that's kind of easy to see, like you could imagine any arbitrarily large matrix with a bunch of variables. if one of these rows is just some number times this guy, yeah, I'm running out of room, to G, then when you go to row reduce this guy and you go to get a 0 here, you'll have to multiply that guy by -2 in order to get -2a, -2b, -2c, and so on. And then adding him to there will give you a row of zeros. But with the more variables, there's more ways of having a linear combination of your equations or of your rows.
So the general principle is this, and you can see why I didn't bother to go into this in class, because we don't really need this for algebra 2. This is something you will talk about ad nauseum if you take linear algebra, or maybe your university calls it matrix algebra. But this is the principle, okay? If one or more equation in a system is a linear combination of some number of, it doesn't need to be all of them, it might just be one or two, it might be one, in which case it's just a multiple of it, it might be many of them, it might be all of the others, but is a linear combination of the other equations, then the system is dependent. That is the definition of what dependent means. And you will get a row of zeros when you row reduce the matrix. That's pretty obvious from what we did before, and it's hard to prove in general without the tools of linear algebra. But it's kind of easy to see, right, just by what we had before, when we took two rows and multiplied them by some numbers and then got a new row out of it. When we were row reducing, we ended up, our algorithm for row reduction just kind of undoes each of those steps, right? It's like, oh, multiply by -2, then subtract that row from that row. Oh yeah, that's just undoing the addition that we originally did. And so that's what's going to happen. That's how you get a row of zeros. So in pictures, this is kind of how we think about it. It's saying if one of your equations or rows is a linear combination of the other. So I'm imagining I have k equations, 1, 2, 3, all the way up to k. And then we make a new one, equation number k plus 1. We do that via a linear combination. So we're taking some constants, a1, maybe that's 2, a2, maybe that's 7. And I just multiply them by the original equations or rows, add them all together to get a new row. And we'd say that this equation is a linear combination of the other equations. That means it is the same thing that ek plus 1, this new equation that we got, is linearly dependent on the equations e1 up through ek.